Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mosaic Works studios. And today I have a very interesting white paper for you, a white paper from Google arguing that we should probably quit doing microservices and do instead something else. And I found it very interesting, and I'm gonna go into details and react to it and add my comments and my insights. But before we're doing this, today is a momentous occasion. I'm recording this on the exact birthday of Mosaic Works. We have been around for 16 years now, and we've been working with a bunch of different countries, clients from multiple continents. I actually had a learning program recently that happened online with people from 3 continents. It was quite fun. And it's really something that I wanted to share with you. I am very proud of what we've been doing through the years, and the learning programs and the insights that we created and the innovation that we brought in. And we have some very interesting plans for the future as well. So there's much more of us that will happen. And I really wanted to share this with you because you are a part of what makes this also special. Okay, time to go to our content. And this all started with a tweet from Dr. Milan Milanovic. If you are not following Dr. Milan Milanovic, find him somewhere on LinkedIn, on Twitter, on I think he's on Mastodon as well. He's posting a lot of insightful tweets. He also has a newsletter, and so really interesting person to follow if you're interested in software engineering and software development. Highly recommended. And he posted a summary of a recent paper by authors from Google that found that most of their developers split binaries from one of the following reasons: it improves performance for tolerance and abstraction boundaries and allows for flexible rollouts. Yet splitting applications into microservices has its challenges. And we are going to go through the white paper. I like to go through the actual first-hand source and see what we can make out of this. The paper is called Towards Modern Development of Cloud Applications. The authors are... Okay, this is going to be difficult. Sanjay Gemawat, Robert Grandel, Drian Petrovic, Michael Whittaker, Parvin Patel, Ivan Posva, Amin Vadat from Google. I probably mispronounced some of the names. I'm sorry for that. Let's go into the details. And the general idea, it starts by saying that the problem is that microservices, if you want to split into microservices, there are some challenges. When writing a distributed application, conventional wisdom says to split your application into separate services that can be rolled out independently. This approach is well-intentioned, but a microservices-based architecture like this often backfires, introducing challenges that counteract the benefits the architecture tries to achieve. Fundamentally, this is because microservices conflate logical boundaries, how code is written, with physical boundaries, how code is deployed. I've been thinking about this for a while, and honestly, I believe that microservices came at a point when we didn't have modules with strong boundaries in most programming languages. We now start to get some of those, but it's not as nice or as good as it seems to be. So fundamentally, our problem is to take a large problem, to split it into smaller things that optimize for cloud costs and so on. Now, Google, maybe they may not discuss about cloud costs because they have their own cloud. But if you are deploying on AWS, on Google Cloud, and so on, you will consider how to optimize the costs. And one way to optimize the cost is to make sure that your application is using the minimum infrastructure that it can at every point in time, so that it gets adjusted in real time and you only pay for what you use. And so you use as little as possible. This was also before serverless. And so this was one of the ideas with microservices. How about we optimize cloud costs? How about we manage to scale up and down with varying demand? But there was another thing which many people don't understand, and that is take advantage of Conway's law. Conway's law fundamentally says that that your architecture is determined by the architecture of communication inside your organization. So simple examples, if you have a team of developers that is collocated, they will tend to build a monolith. If you have a team of developers in Romania, a team in Australia, a team in India, a team in US, they will tend to do their own things and communicate through some kind of APIs or interfaces. But that's just let's say, the simplest example of Conway's law in practice. And so one thing you can do is to take advantage of Conway's law instead of fighting with it. And that means starting from the idea that you want to you want to finish a project very quickly. And in order to do that, what you need is to scale up the number of people who work on the project very quickly. And the way to do that is to take the architecture, to split it into smaller things, give each of the small thing to one pair of developers, and every small things communicate through each other through an event bus, which means that they are completely decoupled, which also means that the people are completely decoupled, so they can actually work in parallel, and you can achieve massive parallelization in the number of teams that you use, because you actually use the Conway's law in your advantage, and you build the architecture communication in the same way with the people communication, the organizational communication. So that's the general idea and the general gist of it. And so there are some good contexts when microservices are useful. But really, the question is, could you have achieved the same thing in a different way if we had a different technology? And I think the answer is yes. And that's basically what they are saying as well. Because nothing tells you that you need to have multiple binaries. The only reason why we need to have multiple binaries is because we don't have the notion of module in our programming languages. If I could write, this is a module, these are the things contained in this module, and I can compile this module separately so that I can run it for myself and test it locally and test it on our own infrastructure and so on, if I'm the Romanian team, let's say. But if I am the team in US does the same. But then there's a simple way of getting all of this together in one binary and deploying it as one thing, and that thing would be, bring modules together, right? It should be as simple as that, but we don't have that. And it's pretty weird that we don't, honestly. It's a big lack of feature from our programming languages. And I know Java has tried to do something around modules. C++ is doing some work around modules. But today is still unclear whether we have those or not. Python is doing some work with modules, and well, modules have been part of Python from the very beginning. But in Python, we have problems with packaging. It's quite ugly, I believe. So the whole problem is not solved in any technology right now. And you can work around it, but it's not out of the box for you. So that's one of the big problems. So then based on that, what can we do? Well, we can create services, they scale up and down, and we can have these binaries, and then we need a way to communicate that is uniform, and we choose HTTP and we choose REST, because REST is kind of the uniform way of accessing HTTP, of doing HTTP applications. So yeah, and we end up with this, with what we have today with microservices. But the question is, couldn't you have done the same thing differently? And let's not forget, one challenge with the one binary is the resources it uses, particularly when you are doing this on the cloud. And again, Google has their own cloud. They probably don't care about the infrastructure costs, but they should care. Many other organizations do care. If you have your own cloud-like system, maybe you don't care as well, or you care less. But if you pay to AWS, if you pay to Google Cloud, if you pay to Azure, Microsoft Azure, then you will care about how much of this you are using. So really, a single binary might work in some cases, but not in all cases. Okay, but it's very interesting how they put it. So microservices conflate logical boundaries with physical boundaries. Logical boundaries, how code is written, with physical boundaries, how code is deployed. Okay, and those two shouldn't necessarily be the same, right? I mean, you should be able to have logical boundaries inside the physical boundary. It's obvious. And that's what I would call a module that is deployed inside a monolith, for example. In this paper, we propose a different programming methodology that decouples the two in order to solve these challenges. With our approach, developers write their applications as logical monoliths, offload the decision of how to distribute and run applications to an automated runtime, and deploy applications atomically. Our prototype implementation reduces application latency by up to 15% and reduces cost by up to 15 times, sorry, and reduces cost by up to 9 times compared to the status quo. Okay, these are pretty large numbers. I'll have to judge this a little bit. So I'm curious what they used as prototype implementation and what they used as numbers. It sounds a lot, honestly. I mean, application latency, I can understand that, because particularly when you have for a single request to go through an event bus and then through multiple microservices, yeah, you'll have latency. That's a given. You can probably use something like gRPC to reduce latency, but it's not that much. HTTP3, or what was the number? I don't remember. The one that keeps connections alive, maybe. Might help. So I'm curious what they are comparing with. Are they comparing with the usual HTTP 1.1 standard latency ridden XML or, well, JSON REST implementation? Or did they also try to optimize using the various ways with gRPC and with HTTP2? Our prototype implementation, okay, well, we read this, cool. Cloud computing has seen unprecedented growth in recent years. Writing and deploying distributed applications that can scale up to millions of users have never been easier, in large part due to frameworks like Kubernetes, messaging solutions, and data formats. Like, okay, and they use the references. So let's see, messaging solutions. I imagine we're talking about Kafka. Yeah, probably. Cloud Map Kafka. All right. Bunch of different things. And data formats. The prevailing wisdom when using these technologies is to manually split your application in separate microservices that can be rolled out independently. Via an internal survey of various infrastructure teams, we have found that most developers split their application into multiple binaries for one of the following reasons. It improves performance. Separate binaries can be scaled independently, leading to better resource utilization. Is performance and resource utilization the same thing? Normally, I will measure performance in terms of response time. And resource utilization is for me a different thing, is about infrastructure costs. Well, when we are talking about cloud, otherwise it would be, yeah, it's a kind of optimization, but not, I wouldn't call it performance. 2, it improves fault tolerance. A crash in one microservice doesn't bring down other microservices, limiting the blast radius of bugs. 3, it improves abstraction boundaries. Microservices require clear and explicit APIs, and the chance of code entanglement is severely minimized. Yeah, you don't have spaghetti code, but you can have dependency hell between microservices. When you have a tree of direct calls between microservices, which would be in direct contrast with what I was talking about before, event-based architecture. 4, it allows for flexible rollouts. Different binaries can be released at different rates, leading to more agile code upgrades. However, splitting applications into independently deployable microservices is not without its challenges, some of which directly contradict the benefits. It's very difficult to find the actual correct microservices, and well, you'll never find the correct ones, you'll find the least bad ones, maybe at best. So yeah, you will have some issues with that, particularly since you have to deal with so many things that are contradictory. On one hand, I need to be able to deploy separately to scale up and down, but we also need performance. We might need transactions. It starts to get really complicated after a while. Okay, let's see the problems. It hurts performance. The overhead of serializing data and sending it across the network is increasingly becoming a bottleneck. When developers oversplit their applications, these overheads compound, yeah. C2, it hurts correctness. It's incredibly challenging to reason about the interactions between every deployed version of every microservice. Yeah, so that's the biggest problem. We basically moved the complexity from a single binary to multiple binaries, which just makes things a lot worse. With this being said, contract-based testing, these are the important things that you can do. In a case study of over 100 catastrophic failures of 8 widely used systems, 2/3 of failures were caused by the interactions between multiple versions of a system. Yeah. And one thing they did, I remember in one of the case studies, was that they were having a special monitoring object that would take answers from different versions of a microservice and pick the one that fits based on different strategies. And that is something that might work. But then we also need to do some more complex chaos engineering, basically. So you know that the whole system is complex and it will go down. So then let's start taking down some services and see what doesn't work, what blows up. And that's a kind of testing that Netflix does. It's hard to manage. Rather than having a single binary to build, test, and deploy, developers have to manage n different binaries, each on their own release schedule. Running end-to-end tests with a local instance of the application becomes an engineering feat. Well, probably because you shouldn't be doing that. I mean, look, there are ways of dealing with this. I understand what they are saying. But really, running end-to-end tests for a whole microservice-based infrastructure, not the best way. What I would be doing is a kind of, I think it's called blue-green. I always forget. Red-blue deployment, something along those lines. So I have version N and version N+1 of the same microservice. And for a while I get answers from both, but the only thing that I'm doing is comparing the answers and making sure that I get the same thing. And I do this for a while. And only afterwards I promote VN+1 as the nominal one, the one that is, picked as an answer. But yeah, it is hard to manage either way, because this is also something that's hard to manage. It freezes APIs. Once a microservice establishes an API, it becomes hard to change without breaking the other services that consume the API. Legacy APIs linger around and new APIs are patched on top. That's not quite correct. I mean, this is only correct if you are doing direct calls to microservices. And that's when my problem is, because then you have coupling between microservices, and this is basically a coupling problem. If you have events, it's not the case, because with events, what you do is you have V1 event, so VN event, VN+1 event. VN event is processed or message, it doesn't matter. It can be a message. So message VN is processed by the current version of all microservices, and they know how to do everything. And then you go to VN+1, which may be, let's say you add a field. And by the way, you should use refactoring, which means you need to add a field first and then remove the older one if you want to change its meaning, for example. So you add a new field to the message. If you add a new field, in general, nothing should break. So you could switch to VN+1, only it will not take into account the new field. But let's say you add a new field and you also need the answers to be different. You then move every other microservice to the VN+1, or the central thing that does the event processing. So if you base your microservices on events, this becomes easier. Not simple, okay, but it doesn't freeze the APIs. If you are doing direct calls, then once again, you need to use exactly the same thing, refactor APIs. So, and I think we discussed about this. I have a whole video on parallel change. You never change a public method in the API, you add a new method, and then you remove the older one after all the dependencies have been updated. That's basically how you do it. But if you have versioning, you will have V1, V2, and so on. But yeah, you need skills and you need the discipline to actually do these types of things. So yeah, it's hard. It slows down application development. When making changes that affect multiple microservices, developers cannot implement and deploy the changes atomically. They have to carefully plan how to introduce the change across n microservices with their own release schedules. Well, you see, this is where it gets tricky because so when making changes that affect multiple microservices, in general, you shouldn't have changes that affect multiple microservices. At least not at the same time. I mean, not time bound. That's one of the way of, if you go into this world, this is what you are getting yourself into. So you have VN of the microservice running, you deploy VN plus one. At their own time, the callers of VN of this microservice need to switch to VN plus one, and so on. If it's based on events or messages, it's even better. And then what you need to do is to distribute. I think one of the challenges is also that you split the teams, and each team has one microservice they can work on, or 2 or 3 or 10. When instead what you need to do is to change the way you plan so that you distribute changes to the microservices depending on the bottlenecks. If a team is taking too long to make an implementation, you need to find another team that has spare time and do that. And I know it's a bit weird to say spare time. It's more about prioritization, right? It's about prioritizing what's important. So if this is something important, then you prioritize it against the other things, and you say, okay, so this team needs to pick up the slack and they need to do this, even though it might not be at the same speed because they need to learn a bit more. Yeah, absolutely. But it needs to be a little bit more dynamic than how it is today. And it helps if your services are really small. Oh, by the way, another thing you can do is basically rewrite that service. Because let's say you have a microservice that's written, I don't know, in Python, but then you want a Java team to pick it up. And okay, I'm a polyglot programmer. I like to move between worlds, but not everybody does. So let's assume this is the case because this is usually the case. And in that case, one thing you could do is basically rewrite that microservice. And you have the contract test that you can follow to make sure that it's doing the same thing. But remember, these have to be small enough. And by small enough, we mean it can be rewritten in 2-3 days by a pair of programmers. And they should have their own database. That's another thing that's not mentioned here. But if you couple through the database, then it's a bit of a problem. Again, you have coupling, and if you have coupling, you're in a world of hurt because things depend on each other and you cannot change things independently. So do you need to carefully plan? Maybe, but I think you need, if you go into microservice, you need to forget about, you're getting into a different world, and that different world is different with two things. One of them is eventual consistency in terms of how data is processed and shown. The second one is eventual feature delivery. Right? You'll know when you start. You'll know it will distribute between the different teams. But trying to predict when it will end, that's a bit of a challenge. So if you want that kind of thing, and it's much more important than all the other advantages of microservices, pick something else. In our experience, we have found that an overwhelming number of developers view the above challenges as a necessary part of doing business. Many cloud-native companies are in fact developing internal frameworks and processes that aim to use some of the above challenges but not fundamentally change or eliminate them together. Yeah, that's always the case. For example, continuous deployment frameworks simplify how individual binaries are built and pushed in production, but they do nothing to solve the versioning issue. If anything, they make it worse as code is pushed into production at a faster rate. Various programming libraries make it easier to create and discover network endpoints, but do nothing to help ease application management. Network protocols like gRPC and data formats like protocol buffers continually improve, but still take up a major fraction of an application's execution cost. Yeah, so they mentioned this. There are two reasons why these microservices-based solutions fall short of solving challenges C1-C5. The first reason is that they all assume that the developer manually splits their application into multiple binaries. This means that the network layout of the application is predetermined by the application developer. Moreover, once made, the network layout becomes hardened by the addition of network encoding to the application. Networking endpoint, client server stubs, network optimized data structure. This means that it becomes harder to undo or modify the splits even when it makes sense to do so. This implicitly contributes to the challenges mentioned above. The second reason is the assumption that application binaries are individually and in some cases continually released into production. This makes it more difficult to make changes in the cross-binary protocol. Additionally, it introduces versioning issues and forces the use of more inefficient data formats. This in turn contributes to the challenges listed above. In this paper, we propose a different way of writing and deploying distributed application. Our programming methodology consists of three core tenets. 1. Write monolithic applications that are modularized into logically distinct components. 2. Leverage a runtime to dynamically and automatically assign logical components to physical processes based on execution characteristics. 3. Deploy applications atomically, preventing different versions of an application from interacting. And yeah, I just wanted to say that this is very similar with the actor system, but they actually mention it in the next paragraph. Other solution, e.g. actor-based systems, have also tried to raise the abstraction. However, they fall short of solving one or more of these challenges. Though these challenges in our proposal are discussed in the context of serving applications, we believe that our observations and solutions are broadly useful. The idea is good. I will give them that. Having a monolithic application that you can split into logical modules. Yes, exactly. Precisely what we are saying. And then forgetting about how this runs because it automatically distributes in a runtime. This is actually great. Now, there are some caveats with this. And the thing is, if you're running on the same computer, it's easy, right? It's very likely that you can do this runtime. It's not extremely simple. You may still have some challenges, but basically you can start the process for various components and you can communicate between processes. Everything needs to be serializable between processes, which is something that's not necessarily true in process. So there's that first. But okay, I think you can deal with this. I imagine you'll have some weird issues. If things are not serializable or if it tries to serialize them automatically and you get some weird errors and you don't know where they come from, so you can end up with this. But it's not the end of the world. These are things that you can probably figure out. The interesting thing is if you try to run this in a cloud-based system, and there what you could do is to deploy, let's assume you deploy every component as a serverless thing, as a function, you start to get other things. So you start to get, and we did a video on assumptions about distributed architecture. It looks to you as if it's a monolith, but when you run it, it might give you issues related to distributed problems, like the networks might fail and so on. So I have a bunch of questions because this runtime, while it sounds really cool, could it manage to deal with these reliability issues? I don't know. Let's see. Okay, proposed solution. The two main parts of our proposal are a programming model with abstractions that allow developers to write single binary modular applications focused solely on business logic. Completely agree with this. I want this. This might be the most important thing we can do for programming languages today. And two, a runtime for building, deploying, and optimizing these applications. Okay. The programming model enables a developer to write a distributed application as a single program where the code is split into modular units called components. We could call them modules. Okay. This is similar to splitting an application into microservices, except that microservices conflate logical and physical boundaries. Our solution instead decouples the two. Components are centered around logical boundaries based on application business logic, and the runtime is centered around physical boundaries based on application performance. For example, two components should be collocated to improve performance. Oh, okay. So basically define how they are deployed, I think. This decoupling, along with the fact that boundaries can be changed automatically, addresses C4. C4 was freeze of API. Okay. Yeah, it makes things easier. So I will give them that, because if you can change things into one single place, you can also take advantage of refactoring tools. There are a bunch of things that you can have. So it's very powerful if you can get this correctly. The challenge is still getting the runtime to be reliable and performant and reduce costs and all that. By delegating all execution responsibilities to the runtime, our solution is able to provide the same benefits of microservices, but with much higher performance and reduced costs. For example, the runtime makes decisions on how to run, place, replicate, and scale components. Okay. Because applications are deployed atomically, the runtime has a bird's eye view into the application's execution, enabling further optimizations. For example, the runtime can use custom serialization and transport protocols that leverage the fact that all participants executed the same version. Writing an application as a single binary and deploying it atomically also makes it easier to reason about its correctness. It makes the application easier to manage. Our proposal provides developers with a programming model that lets them focus on application business logic, delegating deployment complexities to a runtime. Finally, our proposal enables future innovations like automated testing of distributed applications. Oh, interesting. Yeah, I guess you can do that. Okay, let's see. Programming model, components. The key section of our proposal is the component. A component is a long-lived replicated computational agent similar to an actor. And by the way, this is very similar to the initial vision of object-oriented programming. I've long argued that microservices are basically objects. And that's how you should look at them. Every object has an IP, and you call that object. And you should apply the same principles that you apply for object-oriented programming to microservices. plus some additional ones due to the distributed nature of the deployment. But other than that, it's the same thing. And this is basically what Smalltalk had. They had long-lived objects. And you could add you'd start the runtime and then add your object to the runtime and then start interacting with existing objects. And that's basically what they are proposing. So it sounds very Smalltalky. Each component implements an interface, and the only way to interact with the component is by calling methods on its interface. Components may be hosted by different OS processes, perhaps across many machines. Component method invocation turns into remote procedure calls when necessary, but remain local procedure calls if the caller and callee component are in the same process. Components are illustrated in Figure 1. The example application has 3 components, A, B, and C. When the application is deployed, the runtime determines how to collocate and replicate components. Okay, so A, B on the same place, C is actually deployed 2 times. And okay, we have a bunch of a hello world application that has a component interface and a component implementation, and don't recognize this syntax. Is this TypeScript or something like that? I don't know. But okay, I mean, that's fairly reasonable. Components are generally long-lived, but the runtime may scale up or down the number of replicas of a component over time based on load. Okay. Similarly, component replicas may fail and get restarted. Oh, that's very important. Yeah. Cool. The runtime may also move component replicas around, example, to collocate 2 chatty components. Oh, that's cool. In the same OS process, so the communication between the components done locally rather than over the network. Yeah, I like this. I mean, there are two things about this. There is an advantage and a disadvantage. The advantage is that you forget about the optimizations, because the runtime does optimizations for you. The disadvantage is that with every type of magic that you add, you raise the abstraction. So you are counting on this thing working. When this thing doesn't work as you expect, it's very difficult to figure out why. But in general, I find it a very compelling idea until now. So it's a trade-off by all means, but it's a very interesting trade-off. For the sake of concreteness, we present a component API in Go. Do our ideas are language agnostic? Okay. So this was Go. Okay. Let's go to the runtime. I think the code is pretty clear. Underneath the programming model lies a runtime that is responsible for distributing and executing components. The runtime makes all high-level decisions on how to run components. For example, it decides which components to collocate and replicate. The runtime is also responsible for low-level details like launching components onto physical resources and restarting components when they fail. Finally, the runtime is responsible for performing atomic rollouts, ensuring the components in one version of an application never communicate with components in a different version. How would you get to this place? Components in one version never communicate. How would you, I mean, maybe if you deploy side by side VN and VN plus one? I don't know. There are many ways to implement a runtime. The goal of this paper is not to prescribe any particular implementation. Still, it's important to recognize that the runtime is non-magical. I was talking about magic before, so it's good to know. In the rest of this section, we outline the key pieces of the runtime and demystify its inner workings. Code generation. The first responsibility of the runtime is code generation by inspecting the implements the embeddings in a program source code. The code generator computes the set of all component interfaces and implementation. It then generates code to marshal and unmarshal arguments to component methods. It also generates code to execute these methods as remote procedure calls. The generated code is compiled along with the developer's code into a single binary. Yeah, so some code will be generated, and it might also be a security issue. So we'll have to see. If anybody implements this, we'll have to do a lot of research to make sure that security is on par. Application runtime interaction. With our proposal, applications do not include any code specific to the environment in which they are deployed, yet they must ultimately be run and integrated into a specific environment. Example, across machines in a on-premises cluster or across regions in a public cloud. To support this integration, we introduce an API that isolates application logic from the details of the environment. The color of the API is a proclet. I like how everybody invents their own thing. Every application binary runs a small environment agnostic daemon called a proclet that is linked to the binary during the compilation. A proclet manages the component in a running binary. It runs them, starts them, stops them, restarts them off. Yeah, so you basically need a supervising process if you do this, because something needs to restart and so on. So the implementer of the API is the runtime, which is responsible for all control plane operation. The runtime decides how and where proclets should run. For example, a multiprocess runtime may run every proclet in a subprocess. SSH runtime may run proclets via SSH, and a cloud runtime may run proclets as Kubernetes pods. Oh boy. Concretely, proclets interact with the runtime over a Unix pipe. Okay. For example, when a proclet is constructed, it sends a register replica message over the pipe to mark itself as alive and ready. Periodically issues components to host requests to learn which components it should run. If a component calls a method on a different component, the proclet issues a start component request to ensure it's started. All right, so I think I'll skip the next thing because these are very specific things. But we understand in general that we have a supervising process that kind of manages this whole thing and knows how to deploy to various places and how to communicate. Cool. Atomic rollouts. Developers inevitably have to release new versions of their application. A widely used application approach is to perform rolling updates so the machines in a deployment are updated from the old version to the new version one by one. During a rolling update, machines running different versions have to communicate with each other, which can lead to failures. Ah, I see. So that's the reason. But is this how you should be doing? I mean, you should be doing some kind of red, black. I never remember the colors. Red, blue, red, black. Black, blue, I don't know. To address these complexities, we propose a different approach. The runtime ensures that application versions are rolled out atomically, meaning that all component communication occurs within a single version of the application. The runtime gradually shifts traffic from the old version to the new version. Yes, that's how you do it. But once a user request is forwarded to a specific version, it's processed entirely within that version. Blue-green. Okay. Blue-green deployments, they said. So I missed all the, all the options. I never remember these colors. Part of this is, okay, I understand green. Green is the one that's working. But what is blue? Why do we see blue as, or blue is the one running and green is the new one? I don't know. The metaphor is lost on me. So yeah, that's interesting. One challenge here. What happens with logins? What happens with, do you lose packets? Can you do this without downtime? This is interesting. I don't know. So I guess it depends a lot on what the runtime can do, but some of the things will be specific, and I think you might need to write some, so the runtime should be extensible so that you could run and plug in some of your own code for things that are specific to your product, related to deployment. Enabled innovation. So we discussed the problem, we discussed the solution, and now what they are talking about is things that are enabled if we go into using these types of method. And it's quite interesting. Let's see. Transport, placement, and scaling. The runtime has a bird's eye view into application execution, which enables new avenues to optimize performance. Yeah. And I think we covered that already. I like this. I think this is a big advantage. It's a big advantage over the current version of microservices. It's a more dynamic one. There are some challenges though. Security might be one. Can you kid this into deploying someplace else where you shouldn't? I don't know. So it's definitely a very promising thing. Definitely something I'd be interested in entertaining and in trying out and using. But it depends a lot on the implementation, as expected. So, routing. The performance of some components improves greatly when requests are routed with affinity. For example, consider an in-memory cache component backed by an underlying disk-based storage system. The cache hit rate and overall performance increases when requests for the same key are routed to the same cache replica. Yeah, so indeed, that's a good one. And that's also a performance, right? Performance thing. Because we optimize the response time by routing in different ways. Cool. Automated testing. Now, this is one of the most interesting parts. By the way, you can do automated testing for microservices. And particularly when you do event-based microservices, it's quite easy. You need the event in, event out. They have their own database, so you can basically run write tests for the whole microservice, and then you need some contract-based tests. And yeah, and that should cover most of it. You cannot do end-to-end very easily, but that's another problem. Probably would go straight to either to the interface, to the user interface, and you do something like Selenium. Not great. I don't particularly like this because it's slow. But you can go one level beyond that and call the server. Basically do end-to-end testing with server calls. One of the touted benefits of microservice architecture is fault tolerance. The idea is that if one service in application fails, the functionality of the application degrades, but the app of the whole remains available. I just wanted to say this is not completely correct. You have to plan for it. And that's basically what they say next. This is great in theory, but in practice it relies on the developer to ensure that their application is resilient to failures, and more importantly, to test that their failure handling logic is correct. Yes, and that's why you need chaos monkeys, chaos gorilla, chaos engineering. Testing is particularly challenging due to the overhead in building and running and different microservices, systematically failing and restoring them, and checking for correct behavior. As a result, only a fraction of microservice-based systems are tested for this type of fault tolerance. That's true. So, testing for fault tolerance, while I'm talking about Chaos Monkey, Chaos Gorilla, Chaos Engineering, the technique is good. The costs and time in doing that, it requires some investment. Let's put it this way. With our proposal, it is trivial to run end-to-end tests because applications are written in single binaries in a single programming language. End-to-end tests become simple unit tests. Okay. This opened the doors to automated fault tolerance testing akin to chaos testing, Jepsen testing, and model checking. Let me think a little bit about this. So applications are written as single binaries in a single programming language. End-to-end tests become simple unit tests. That's not entirely correct. By the way, I just realized we haven't talked at all about the storing data. And that's a bit of a problem. How do you do with databases? Does each of the component have its own database? How do you deploy those? How does the runtime know to deploy the database in the right place? I mean, okay, you could use a RDS or some kind of cloud database service. But okay, hello world is easy, but if you go over it, it's unclear. So I don't like the mix between unit test and end-to-end test. The unit tests test one behavior, have a single reason to fail, or as few as possible. If you do end-to-end tests, it's not unit tests. So let's first of all make this very clear. Now, you might use the same framework to write the end-to-end tests, and that's an advantage that you don't have with microservices, and I think that's what they are trying to say. And that's good. Now, my problem is, how does this deal with the different types of deployment? So I could run unit tests with a deployment that is a monolith single process, or multiple processes on one machine, or distributed across multiple machines. These unit tests and these end-to-end tests might sometimes fail due to the underlying deployment model. And that's when things start to get ugly, because you have tests that sometimes work, sometimes don't. Not that great. However, I understand what they are saying. We could do automated fault tolerance testing, because what you do is you basically start the application, deploy it, have your end-to-end tests run as monitors, basically run in a loop, and they just call the same things again and again, and then doing all kinds of simulations of breakdown. So you take down one component, you take down another component, and you see how long it takes for the end-to-end test to return to pass from fail. And that gives you the resilience numbers, the mean time to fail, not mean time to failure, the other one, mean time to restoration or something like this. Okay, so that's a really good thing, but let's not conflate end-to-end tests with unit tests, please. Stateful rollouts. Our proposal ensures the components in one version of the application have communicate with components in a different version. This makes it easier for developer to reason about correctness. However, in the application updates state in a persistent storage system like a database, then different versions of the application will indirectly influence each other via the data they read and write. These cross-version interactions are unavoidable. Persistent state by definition persists across version, but an open question remains about how to test these interactions and identify bugs early to avoid catastrophic failures during rollout. Yeah. You see, when you start getting the data in, things start to get a little bit muddy, and it's not clear how many. I mean, ideally you'd have each component with its own database, right? And that would be very interesting. Okay. Innovation in the area discussed in this section is not fundamentally unique to our proposal. There has been extensive research on transport protocol routing, testing, resource management, troubleshooting. However, the unique features of our programming model enable new innovations and make existing innovation much easier to implement. Okay, I think that's fair. Prototype implementation written in Go. The code generator, a Proclet architecture, it uses TCP, also comes with a Google Kubernetes engine deployer. It uses horizontal pod autoscalers and is available at github.com/serviceweaver. Okay. Serviceweaver. All right, so it's called Weaver. You can actually take it from GitHub, serviceweaver/weaver. Really cool. Okay, it's good that we have it. To evaluate our prototype, we use a popular web application representative and so on. The one generator. All right. So they are talking now about how they did the evaluation. But I'm gonna skip on this because I think there's a lot that we discussed, and that's fair. That's quite enough. And if you want to learn more, you can read the paper. The link will be in the description. You can also check out the implementation. The link will also be in the description. Cool. So what are my feelings at the end of this? Let me think. I think the idea of having modules with strong boundaries inside one binary is great. And then you only take it to the next level if you say, let's have a runtime that can deploy this and kind of generate the glue code and all that. The challenges are in terms of developer experience. When things don't go well in the runtime, it will be very difficult to figure out what and why. But everything else is simpler. So these are good things. I would be a bit worried about security, because you add an additional thing that can create security breaches with this runtime. And I'm also thinking whether you can have things like zero trust between microservices, between these components. So imagine you deploy the one component, they are defined in a big thing, okay? But you can define this component needs to go into one place, this needs to go into another place. How do you do authentication between these? It would be great, but that would be maybe a tall order for this runtime. If you could also add certificates-based authentication with this. So yeah, things start to get quite muddy. You also need to be able to define permissions somehow. This is where there's a problem with metaphors in software development. Metaphors and abstractions. Let's talk about abstractions. Kind of the same thing, but let's talk abstractions. Abstractions work up to a place, and when you go over that, they break. So if you abstract the notion of module, and you think, ideally it would be one thing and I don't care how it runs and so on. Problem is, we still do care how they run. Because depending on how they run, if they run in the same binary, it's one thing, but if they run in different processes, a bit more complicated. If they run in completely different places in your infrastructure, it starts to get really muddy. So could you test, for example, security issues between components with this model? Because you don't particularly know what's created there. And I guess if the protocol is strong enough, but every protocol has a potential for injection attacks. And so you need to be careful with this. Yeah. So honestly, I have mixed feelings. It sounds like a great thing in theory. I really believe we should be able to define our modules in a nice way. But I think it's more likely that we'll end up, instead of having this smart runtime, I would be happy just being able to define, this is my solution, let's say. These are the modules. Each module has its own thing, but then each module I can also define how it gets deployed, what do we add on top as glue code, as protocols, and all that. I would be very happy with adding the API on top of that, kind of like a configuration for the module. Even if this means writing a bit more code, but you have slightly more control over what's happening in deployment. And so the first step would be the ability to define these modules and to kind of being able to run them locally with a specific configuration, being able to run them remotely with a different configuration. So I'd be happy if we just managed to do this. The ideas are very interesting. And the small talkie approach sounds really cool. But I still see a lot of challenges with this. So, should you switch from microservices? That depends. How did you write your microservices? Are they really micro? Are they really following the design principles for objects and not only? Think about that. I think realistically, people will still live with microservices for 5 years. If we start switching today to another model, it will take at least 5 years to do that. And we don't have a model yet. So it's going to take even longer, right? So I think microservices are here to stay, if not as something else than as legacy code. Although with microservices, you also got a lot of reorganization in companies. You got a lot of practices that were introduced. You got a lot of, automated infrastructure. So quite a lot of things that companies have invested in and they want to take advantage of. So I don't think people will skip and will jump, even if today we have this magical solution, a runtime that runs perfectly nice. I don't think we'll jump straight to it. But I do believe that developers, architects are starting to look at other ways of splitting applications. But all in all, the best thing you can do as a developer or as an architect is to figure out what are the modules, how to identify modules, that can be separated. Basically, they can be separated, they can be replaced, they can be put together, they can be reshuffled into different solutions. That's the best thing you can do. And it doesn't matter what level it is. It doesn't matter whether it's inside of a monolith as its own process, as it's, a Linux service or OS service, or as a service or on another machine communicating through events. The logic is still the same. So that's a hard skill that will work no matter how we end up developing and deploying these applications. Same skill you'll need for everything else. So the lesson of all this is learn how to do modular architecture, learn how to do modular design. All right. That's it from me today. What do you think about all this? Let us know in the comments. What challenges are you facing with your microservices, with your architecture, with your infrastructure? Let us know. I know we have a lot more things to talk about from the comments. Somebody asked if we know tools for C++ that can ensure safety. And honestly, I'm at a loss. I have to ask some people, but if you know some of them, go back to the video about C++, about Herb Sutter, and leave us an answer. Maybe you might know a list of tools or a blog post or anything around this. All right, so yeah, let's talk about software. Thank you kindly for the view, and until next time, remember to think, design, and work smart.